Emil Jeřábek from Czech Academy of Sciences, and he'll talk to us about feasible reasoning with arithmetic operations. Welcome, Emil.
Yeah, thank you. Thank you very much for inviting me. I've never done an online seminar before, actually, so I hope you will be able to hear me okay. Also, I hope that it seems that there may be some problems with my internet connection, so that it will work all right. So let me try to share the slide. Can you see it?
Yes, it's good.
Okay. So yeah, so I gave the talk a fancy title, but what I'm going to talk about will be well, some properties of basically the bounded arithmetic theory VTC 0, which corresponds to the complexity class TC0, and I'm especially interested in what kind of things it can prove about addition and multiplication, the basic arithmetic operations. So, okay, so this is the outline of the talk. First, I will say a bit about why we are doing this and what is TC0 and VTC0 and so on. Then I will speak about open induction. This will be the kind of first result that certain extension of VTC0 proves open induction. I will skip parts 3 and 4, which included more details about the ideas used in the proof, but I originally thought that the seminar would be longer, so we will not really have time for this. And then
Emil, I just want to say that we can always invite you back. So if there is something you would like to say more to us, and we can always split it into parts. So there is no big need. Just go as planned.
So I will do it as planned, and if you are still interested then about hearing the more details, then you can make an arrangement for that. But I think that it will be better to do it this way. That I will first give the like more general overview, and if you are interested in the more technical details, then I can speak about that
okay.
another time. So yeah, so then I will say something about the setup of bounded arithmetic in buses language, which will allow us to extend the result to a certain extent. And the last part, I will talk about the probability of iterated multiplication and division in VTC0. I should perhaps say that most of the talk is based on old research, something that I've done some, I don't know, 5 or 6 years ago, except the last part, which is about unfinished research. So it's kind of, there will not be really a good punchline or anything, but yeah. Here is what some people like to present as a kind of a big picture of what we are doing in proof complexity. Not everybody agrees that this is a good way to present it this way, but the idea is that we study a kind of threefold correspondence between theories of arithmetic, computational complexity classes, and propositional proof systems. Now, I will not talk about propositional proof systems at all in this talk, only about theories and complexity classes. So, in this case, the correspondence, well, it's a kind of a loose, vague term, but what it usually means is that if the theory T corresponds to a class C, then on the one hand, the probable total computable functions of the theory in some useful sense are exactly the functions computable in this class C. And on the other hand, we can reason in the theory using formulas that express properties from this class C, which means that usually this theory is axiomatized using an induction schema or comprehension schema as its main axiom. And so the theory has this induction, comprehension, and related principles for formulas that correspond to properties computable in this class C. So this is a rough idea of how this correspondence between theories and complexity classes is supposed to work. And we can use this to formalize a kind of a notion of feasible reasoning. Namely, if we are given an efficiently computable object, I don't know, function, predicate, whatever, that's computable in this class C, what are the things that we can prove about this concept using again efficient reasoning, or like something that only uses reasoning not exceeding the concept itself, which if we have this theory T that corresponds to the complexity class C, then we can just formulate it as a question: what does this theory T prove about this concept X? And so that I do not just talk abstractly about these kind of vague concepts and so on. In this talk, the concept we are interested in are the elementary integer arithmetic operations: addition, multiplication, ordering. Well, ordering is not an operation, but still. So now the question is, what is the right complexity class for these arithmetic operations, and what is the corresponding theory? So the complexity class will be the class TC0, as I already mentioned, but since this is a kind of exotic class, I will need to let me first say a few general words about what options do we have to define complexity classes. So the most obvious way is that we consider computation on Turing machines or an equivalent computational devices. So these may be deterministic Turing machines, which somehow correspond to the actual computers that we can use, but they may also be more exotic things like non-deterministic Turing machines or alternating Turing machines, randomized Turing machines. So these not necessarily correspond to any actual model of computation. It's just a theoretical model. And typical resources which we study for, in this case, are time and space needed to compute something. So then we have classes of languages that are computable in this and this amount of time on a Turing machine. A different way of defining complexity classes is that we identify a language with a family of Boolean functions. So language is a set of alphabet. I will usually just think about languages over the binary alphabet, where we have just 0 and 1. Then if we look at the nth slice of the language consisting of words of length n, and we can look at this as a Boolean function with n Boolean inputs and Boolean output, which tells us whether the given input is or is not in the language. And this way we have a family of Boolean functions, and then we can look at how these Boolean functions may be expressed by Boolean formulas. So we can define the language by a family of Boolean formulas. Or more usually, people use Boolean circuits. Circuits are basically just like formulas, except that formula is a tree, but the circuit may be a more general graph. In other words, a circuit is a formula where we don't. If you have some subformula that's used several times, we just include it once and do not copy elsewhere. And in this way, we can express it in a small way. But, so the parameters that we can study about these formulas are the size of the formula, the depth, which is like the depth of nesting of the connectives, basis, meaning what kind of connectives do we allow in the formula. So typically we can use conjunction, disjunction, and negation, but we may also use more exotic connectives like parity. And fan-in, meaning whether we just allow binary connectives, or in case of conjunction or disjunction, we also may allow conjunctions of arbitrary number of inputs. And an important thing is that we can describe non-computable languages in some cases by completely trivial formulas, because we have for each length n we have a separate formula. So in order to avoid such pathological cases, we also need to assume that the family of formulas which defines the language is somehow uniform, which means that if we are given n in unary, we can somehow compute the corresponding formula efficiently. I will not go into details what efficiently means here, but this is the idea. And the third way how to define complexity classes is using so-called descriptive complexity, where we identify strings over a finite alphabet with certain finite structures, finite first-order models. So if you have a length, a string like this of length n, and we represent it as a model that has a domain of size n. So the elements in the domain are, say, the integers 0, 1 up to n minus 1. Then we have unary predicates that tell us what letters are at what positions in the string. So this predicate P0 says which of these indices have 0 at them, and the other one, which of them have 1. And then we have some other structure that somehow is needed to fix the, so to speak, identity of the individual elements in the domain, so that we cannot just permute the string randomly or something. So typically, we consider the structure endowed with the ordering relation, but we may also include other arithmetic predicates like addition and multiplication. So what this means here is that we take, say, the graph of multiplication restricted to this domain as a ternary predicate. And then if you want to describe a language, we consider formulas that define this, the corresponding class of finite structures. Then what we can study is, or how we can describe the complexity of this is, first of all, by specifying the logic of where we take this description formula from. It may be first order logic, it may be second order logic, maybe something more complicated. We may also look at quantifier complexity. So now, so here is an overview of few small complexity classes. So these are all complexity classes below polynomial time, including this TC0, which we want to speak about. So I include here a few more other classes so that you have some basic idea how this fits in the hierarchy. So the classes here are well, so P is the familiar polynomial time. L is also a very common complexity class. This just means language is computable in logarithmic space on a Turing machine. And L means non-deterministic logarithmic space. And then the other classes here are usually defined as circuit classes. So the basic class AC0 consists of languages that can be computed by a uniform family of formulas that have polynomial size and constant depth. And if we have constant depth, then in order for this to make any sense at all, we have to allow a conjunction and disjunction of arbitrary arity. And an alternative way to define AC0 is using descriptive complexity. It simply consists of languages definable in first-order logic. If we take a suitable set of these arithmetic predicates that are hardwired into the model, I guess the addition and multiplication as is written here would be the right definition. And we can also define AC0 using Turing machines, namely its language is computable in logarithmic time on an alternating Turing machines with a constant number of alternations. So alternating Turing
Did we lose you?
I'm afraid we lost Emil. Let's wait.
Yes, just summing the input variables modulo 2.
Okay, thank you.
So that would be useful to define a complexity class AC02, which I omitted from this slide. But here we have the definition of TC0, and this also uses an unconventional connective. Namely, the basic way to define this class is just like AC0, using constant depth polynomial size formulas, where we allow majority gates or threshold gates. So we have the majority function that we have an arbitrary number of inputs, and the function tells us whether majority of the input bits are 1 or not. And then there is this is included in this class NC1, which can be defined just as by uniform families of polynomial size formulas, or it coincides with alternating logarithmic time or logarithmic time on alternating Turing machines. So sorry. So the here are some more options how to define TC0. So as I said, the basic definition is by uniform families of formulas of polynomial size and constant depth that use conjunctions, disjunctions, negations, and threshold or majority gates. In terms of descriptive complexity, TC0 consists of languages that are definable in logic FOM, which is first-order logic with majority quantifiers. So we extend first-order logic with a kind of quantifier that can tell us whether majority of the values in the model give a truth value 1 okay, and then there is also something called threshold Turing machine, and we can define TC0 as things that are computable in logarithmic time on a threshold Turing machine using a constant number of thresholds. But this is kind of messy to define. So this is just to give you an idea that this is actually a natural class that that is robust in the sense that we can define it in several different ways coming from different backgrounds. Now, And this class is the right complexity class for arithmetic operations, because if we look at the integers or integer operations on where the integers are given just in binary notation as binary strings, then addition and ordering are computable already in AC0, which is included in TC0. And the multiplication is also computable in TC0, and it is in fact TC0 complete under the suitable notion of AC0 reductions. Mm-hmm. So in some real sense, TC0 is the smallest reasonable complexity class that includes all of these operations. And once we have these operations, then we have TC0, and now actually in TC0 we can do much more about integer arithmetic. We can do iterated addition, which simply means that if we are given a sequence of integers, we can compute their sum. This is relatively easy. What is much more complicated, and it was a kind of result, but it was finally proved, that we can also do iterated multiplication. Using that, we can compute integer division, division with the remainder. And we can compute these kind of elementary operations not just on integers, but also on rationals or Gaussian rationals, say. We can also compute functions that are given by nice power series, like trigonometric functions, logarithm. We can sort of compute exponentially, except that we have to make sure the result is not too large. We can compute kth roots and so on. And in TC0, we can also do other things than arithmetic. One very useful fact is that in TC0, we can do sorting. If we are given a sequence of integers, we can output corresponding sorted sequence. So this is the right class. Now, what about the arithmetic? So the usual theory corresponding to TC0 is this theory VTC0. And this theory is defined in this Zambella-style way of doing bounded arithmetic, which is using a two-sorted theory. So we have one sort for integers, but these should be thought of as corresponding not to the real integers that we think of as being given in binary, but to unary integers. So these are kind of auxiliary indices. It's kind of like in the descriptive complexity setting when we had the first order structures whose domain was integers from 0 to n that were just really indices into the string. Then this is something similar, that these unary integers should be thought of as just indices. We have the basic arithmetic on them, but this is not what we are interested in. We are interested in arithmetic on the binary integers. And so this is the second sort, which are officially finite sets. We can think of them as representing binary integers or binary strings. So the language is superficially similar to the language of second order arithmetic, except for the important difference that in second order arithmetic we usually consider infinite sets, whereas the sets here are bounded. And so we have a predicate which tells us which of these unary integer is in a given set. We have this this operation that given a set computes an upper bound, the least upper bound on the elements of the set. So it's like 1 plus the maximum of the set. And so in this, we will generally consider bounded formulas. So bounded quantifiers here are bounded quantifiers are defined as usual, that we just quantify over numbers less than or equal to some term. For sets, we bound the maximum of the set by again some.
But at the same time, you say they are just indices. So, but in unary, the size matters. In unary, the size of a number is just the number itself. But does it matter? What would it mean for integers to be unary?
So, this is just a way to think about it from the computational complexity perspective, I guess. In the theory, you don't really saying that these are unary doesn't have a meaning, but it's just that when I will say that I have a theory corresponding to TC0, then what I will want that, for example, the probably total computable functions are computable in TC0, and what this will mean is that when we have a function probably total and has the right complexity, then this function may have inputs from both sorts, and this function will be computable in TC0 if we give the inputs to the second sort in binary as usual, and we give them to variables corresponding to the first sort in unary. So in this sense, it corresponds to unary integers, just with respect to computability. As far as the theory itself is concerned, these are just integers. It's, So did I answer the question?
Yes. Thank you.
Okay. All right. Yeah. So I defined what the bounded quantifiers are in this context, and then sigma B0 formulas are defined to be formulas that have bounded first order quantifiers and no second order quantifiers, but they may have second order free variables or parameters. Then more generally, sigma BI formulas are defined that we have I alternating blocks of bounded quantifiers, with the first block being existential. Then this quantifier prefix is followed by a sigma B0 formula. So now here we may have bounded quantifiers that are also second order bounded quantifiers. And then the basic theory that's kind of an analog of Robinson arithmetic in this context or something. And then we have comprehension for sigma BI formulas. So in particular, the kind of basic theory is V0, where we have just comprehension for bounded formulas with bounded first order quantifiers with no second order quantifiers. This sigma B0 comprehension implies sigma B0 induction. For the reason that we have this maximum element function. So if you have a sigma B0 formula, we can use comprehension to define the corresponding set, and then you can just look at the maximum element, and this will give us a maximum number satisfying the formula below some bound, basically. So, and we will also consider sigma 1,1 formulas. So these will be formulas with an unbounded second order quantifier followed by a sigma B0. So these are the kind of formulas that we think of as representing recursively enumerable predicates. So then the theory VTC0 consists of V0, which is the theory that I just defined, plus an extra axiom which says that every set has a counting function. So basically, since we want to compute something like majority, we want to have an axiom that for every set we can count the number of elements in the set. And so this is formalized in such a way that we have a counting function which tells us for every initial segment of the set what is the number of elements in it, and this is given by a suitable recurrence, so we can just state it as a second order quantifier that there exists a counting function that has this and this properties. Then the probability total computable, which means sigma 1 definable here, functions of this theory are indeed exactly the TC0 functions. We have the comprehension, induction, minimization, and so on for TC0 predicates. So we can think of an extension of the language of the theory, so that we have function symbols for all TC0 functions, and then we have sigma B0 comprehension and so on in this extended language in this theory. So what can we do about the elementary arithmetic operations in this theory? We can define addition, multiplication, and ordering on the binary integers, and we can prove that they satisfy some basic axioms. In fact, they satisfy the axioms of discretely ordered rings, so they are reasonably well behaved. But a priori, we do not have any induction for them, for example. So, what kind of other things about these operations we can prove in this theory? And in particular, if we can prove induction for some non-trivial class of formulas for these arithmetic operations. And now there is some kind of a complication. As I said, in TC0 we can compute iterated multiplication and division, but this is quite a complicated algorithm, and we do not know yet if we can formalize this algorithm or prove its soundness in this theory VTC0. So we do not know whether the theory proves this formula expressing totality of division with the remainder. And for this reason, we consider also an extension of this theory where this is given as an axiom. Actually, we will not use division as an axiom, but iterated multiplication. The algorithm for iterated multiplication gives also division, but even though the division looks kind of easier and more natural property, we need the axiom to state the totality of iterated multiplication for some reasons. So, this is the theory that I will work with. VTC0 extended by an axiom which says that iterated multiplication is total. So, yeah, there is some more explanation why we want iterated multiplication instead of division, but I guess I can just skip it. It's not really important. So now we come to the second part concerning open induction. So as I said, we are interested in whether the theory can prove induction for some non-trivial class of formulas. And the kind of weakest such theory is this theory I open defined by Shepardson, that consists of the theory of discretely ordered rings plus induction for open quantifier-free formulas in the basic language of arithmetic. So our kind of first question would be whether VTC0 can prove quantifier-free induction for the operations on binary integers. And there is a kind of criterion how to recognize whether a discretely ordered ring is a model of open induction, which is stated in terms of real closed fields. So just a reminder that an ordered field is a field that's given compatible total order, and a real closed field is an ordered field such that every positive number has a square root and every polynomial of odd degree also has a root. and these are really fields that are elementary equivalent to the real numbers. And every ordered field has a real closure, which is an algebraic extension of the field, which is real closed. Now, the criterion due again to Shepardson states that a discretely ordered ring is a model of open induction, if and only if it is a model of the least element principle for open formulas. And that's if and only if it is an integer part of a real closed field. So an integer part of an ordered field is just a discretely ordered subring that such that every element of the field is within distance 1 from some element of the integer part. Discretely here means that there is nothing between 0 and 1. So,
so the ordering implies that these fields are of characteristic 0.
Right, right. And there is also a more explicit way how to restate this condition, namely that if you have a polynomial with coefficients in this discretely ordered ring, and we know that it switches signs, so we have an interval where at the beginning it is negative and at the end it is positive, then we can pinpoint a number inside this interval where this switch happens. That there is a number where the polynomial is negative and it's positive at its successor.
Beautiful.
Now, this theory VTC0, or its extension with iterated multiplication, has a kind of witnessing theorem, which is really just yet another way how to state this fact that it corresponds to TC0. This theorem says that if you can prove that formula of the form that for every x there exists y that satisfies some sigma 1 formula, then there is a TC0 function that witnesses this existential quantifier and is still provable in the theory. Now, if we apply it to this thing here, so this is a formula of this form. You say that for every u and v there exists z. So here I've written them with lowercase letters, but they should really be uppercase. These are the binary inputs. So when the witnessing function that witnesses this formula here takes these 0 and the coefficients of the polynomial, and it basically gives us a sort of approximation of the root of the polynomial within distance 1. And not hard to see that if you can do that, then if we then pass to the fraction field, we can actually approximate the roots to arbitrary precision. So what one can prove from this is that the basic question whether VTC0 with or without this iterated multiplication axiom proves open induction is equivalent to saying that for every constant d, this theory can prove the soundness of a TC0 algorithm that can approximate roots of polynomials of degree d. So first of all, there exist TC0 algorithms that approximate roots of constant degree polynomials. One can prove this using some kind of Morel's elementary complex analysis. The idea is that if we have this polynomial, then we can locally invert it, consider its inverse function on some neighborhood of a given point. And this inverse function will be given by a power series, and one can check that the coefficients of the power series will be given by will be computable in TC0. They are given by Lagrange inversion formula, and then so this inverse function depends on this like point W, where we decide to center the power series, and then if this center is chosen so that it's close enough to a root of the original polynomial, then the inverse function applied to 0 actually finds the 0, the root. And then we can also construct a polynomial size of points W, where will happen to have the property that some of them is close enough to each other zeros, so we can really have all the zeros in this way.
Just a quick historical kind of.
But as I said, this the algorithm uses lots of complex analysis, so it's not really good for formalization in bounded arithmetic. We don't know how to prove things like Cauchy integral formula and things like this. So what this gives us that open induction is provable in VTC0 extended with all true universal or for all sigma B0 formulas, basically. It turns out that we can actually prove open induction in VTC0 plus iterated multiplication, but we have to do it in a kind of more complicated way. And here is a rough outline of how the proof goes. So it has two ingredients. One ingredient is similar as in the algorithm as I outlined it before, to compute some kind of an inverse function to the given polynomial. So we can formalize a suitable version of the Lagrangian version formula in this theory VTC0 plus iterated multiplication, and then we can use it to prove that we can actually approximate roots of polynomials if the constant coefficient of the polynomial is very small in a suitable sense compared to the other coefficients. This is not a precise statement, but this is an intuition of what kind of conditions are involved here. And then in order to pass from this special case to all polynomials, we do not really construct an explicit algorithm for computing roots, but we use a model theoretic argument that establishes that a given model of VTC0 plus iterated multiplication, model of open induction by using this Jefferson's criterion. So we take the model, which is a discretely ordered ring, as we already know. We consider it it's a fraction field, and yeah, and then the model is an integer part of its fraction field because we can prove this division axiom, and then we consider the completion of this fraction field. I didn't say what this is, but it's a kind of largest ordered field that extends this F with the property that F is dense inside it. And this will ensure that the model is still an integer part of this completion. And now to apply Jefferson criterion, we have to check that this completion is a real closed field. And we can then use the theory of valued fields to figure out that how we find out whether something is a real closed field. Namely, this completion is a really closed field if and only if it is Henselian. It is a divisible value group, and it has a real closed residue field. Now, in our situation, it's easy to check that the value group is divisible And we can make the residue field trivially a real closed field because if you just start with an omega saturated model, the residue field will consist of all real numbers. So, the only thing that's missing is that the completion is Henselian, and for this we can just use the first part. The fact that we can approximate roots of polynomials with sufficiently small constant coefficient will suffice to imply that the completion of the field here is Henselian. So in this way, we will obtain that the discretely ordered thing here is an integer part of this real closed field, and therefore it is a model of open induction. So yeah, so now I will skip about these more details about this proof, and so now we have proved that the theory can prove open induction in the basic language of arithmetic, but it turns out that it can actually prove more induction. But to state this, we need to consider bounded arithmetic in this one-sorted language of Bus. So this is a different kind of bounded arithmetic that we considered before. This really extends the usual language of arithmetic. So we have just a single sort for integers, which correspond to what in the previous theory were the binary integers. We have the standard language of arithmetic, 0, 1, addition, multiplication, and ordering. And we also have as additional function symbols, function symbol for half. It's not really important. We have a function symbol for something like length of the number when written in binary, so it's a binary logarithm. We have this smash function, which is basically a function that grows polynomial in terms of length of the integers involved. It's the main point why we had it. Then we have bounded quantifiers as usual, and we can distinguish also so-called sharply bounded quantifiers, where the bounding term is as this length function as the top symbol. So these are like logarithmically small bounds. Then sigma small b 0 formulas are sharply bounded formulas, so we have only sharply bounded quantifiers. And more generally, sigma bi formulas are that we have I alternating blocks of bounded quantifiers followed by a sharply bounded formula. And the most common theories in this language are the theories Ti2 and Si2 defined by Bus. So Ti2 is some kind of a basic theory plus induction for the sigma bi formulas. And Si2 is a slightly weaker theory where we have sigma bi polynomial induction, which is this form of induction where we don't go from x to x plus 1, but we go from x to 2x, basically, or as it is written here, from x half to x. And there is actually a kind of translation between one-sorted and two-sorted arithmetic, which is called the RSUV isomorphism. So in the two-sorted theories, we had sets and numbers. And now these get translated, the sets get translated to numbers, and the numbers translate to small numbers, so logarithmically small numbers. Then what were the bounded second-order quantifiers now correspond to just bounded quantifiers, whereas bounded first-order quantifiers correspond to sharply bounded quantifiers. So the sigma ei formulas were defined so that they match up. For I greater or equal to doesn't really work for 0. The theories Vi that we had correspond to Si2, again for I at least 1. This theory VTC0 translate to theory so-called delta B1 CR defined by Johansen and Polet. So I'm not going to define what this means. This is just to show you that, that there are some reasonable theories that correspond to what we had before. We also have a theory that kind of corresponds to VTC0 plus iterated multiplication, except that we also have this axiom of choice, but this is not important because it's conservative, or the theory for suitable class of formulas. So when I said earlier that the VTC0 plus iterated multiplication proves open induction for binary integers, what this means more precisely is that it proves the RSUV translation of open induction. And likewise, we can state this in such a way that just this first order theory, C02, directly proves open induction. And now we can generalize these results to the following, that VTC0 plus iterated multiplication proves the translation of not just open induction, but sigma B0 induction in this language of Bus, and even sigma B0 minimization. So this is the least element principle. In this context now, the minimization axiom is actually stronger than induction. It's no longer equivalent as was the case for open induction. Or we can again say that this theory C02 div, which is already like one sorted, just outright proves these sigma B0 induction and minimization schema. And we obtain this by basically by formalizing in VTC0 plus iterated multiplication kind of structural description of sharply bounded formulas given by Manciris, that basically says that if you look at something defined by a sharply bounded formula, it can be written as a union of polynomial element interval, except that we have to take separately residue classes modulo some small powers of 2. So I'm not going to go into the details, but basically using open induction as a kind of base case for quantifier-free formulas, we can, in a suitable sense, formalize this this description, and this will lead to a proof of minimization for sharply bounded formulas in the theory. So this is all for the old results. Now I'll say a few words about the new results. So the question which was left open, VTC actually proves this iterated multiplication axiom. And using the results of Johansen and Polet, one can actually show that VTC0 proves iterated multiplication if and only if it proves the division axiom, even though we don't know whether the division axiom outright implies iterated multiplication. So the question is whether VTC0 can formalize the algorithm for iterated multiplication given by Hesse-Allender and Barrington. So here is a kind of a brief outline of the structure of the Hesse-Allender-Barrington paper. A few more notation. We consider here the function of powering small integers, to logarithmically small integers to small powers modulo small primes. Then if you have a large number, binary, then it's a Chinese remainder representation modulo a sequence of small primes. It's just that they take the residue of this number modulo each prime. And then the algorithm or the argument in the paper has kind of 3 stages. First, we prove that iterated multiplication is in TC0 if we take this powering modulo small primes, small numbers as an extra ingredient. And this works by first converting all these integers to this Chinese remainder representation modulo a sufficiently long list of primes. Then we just multiply the individual residues using this powering function or actually using a kind of iterated multiplication of small numbers modulo small primes, which we can define from this. So we multiply all these residues individually, and then we reconstruct the result back from the Chinese remainder representation. This is the most complicated part of the algorithm, how to do this. So then the second part is that we actually show that this iterated multiplication can be done in this smaller class AC0, provided that the inputs are very small. They are polylogarithmic. Done by just taking this result here and scaling it down. Or else one somehow shows that the things that we need here become AC0 if we scale it down to such polylogarithmically small numbers. And then there is a third step. We show that this powering of small numbers modulo small primes is in AC0. This is obtained by somehow showing that we can express this A to R modulo M as a polylogarithmically long product of polylogarithmic powers of suitable numbers, which we can compute using the second part. And then now we plug the third part in the first part back, and we obtain that iterated multiplication is in TC0 because this extra function that we have here is actually redundant. And the problems with formalizing this algorithm in the theory are multiple, but the first problem is that as you've just seen, the whole thing is a kind of complex structure with multiple interdependent parts. It's not just write down an algorithm and prove that it works. We just do one thing, then we translate it to a smaller setting, and then we somehow do another thing, and then we plug it back, and so on. But so this is just a complication that may not necessarily mean that that we cannot do this. What is a much more serious trouble is that there are lots of so to say chicken and egg problems. So what was first, chicken or an egg? So as I said, the most complicated part of the algorithm is this reconstruction of from the Chinese remainder representation. Now, the analysis of this algorithm for this CRR reconstruction heavily relies on already having iterated multiplication. First of all, the first thing that we do is we consider products of all these small primes, and then we do something with them, and we use divisions all over the place and so on. But we actually need CRR reconstruction and the whole algorithm to define these iterated products and divisions in the theory in the first place. So we cannot really carry out this analysis without having them. Even though the actual argument is not difficult, it's elementary mathematics, but it uses a very concept that we want to define using this algorithm. So it's circular. There are similar kind of problems with this powering modulo function. And then there is another obstacle, namely the algorithm as presented relies on the cyclicity of the multiplicative group modulo prime fields, which is something that's notoriously difficult to prove in bounded arithmetic. We can actually prove it in VTC0 plus iterated multiplication, but it's not clear how to do this without it. And the specific place where this is used is to get like iterated products of small numbers modulo small primes from these from having just these powers, because what we do is we consider like a generator of the multiplicative group, and we can use this powering modulo function to translate between the residues modulo M and like the exponent of the generator that defines them, then we just use iterated addition that we can do in VTC0 to sum them modulo n-1, which is the size of the multiplicative group, and translate it back using this powering modulo. So yeah, so this is another obstacle. So now what I can prove so far is that if we take VTC, is basically we can formalize the first part of this algorithm, but if we sidestep this cyclicity issue by just considering directly this iterated multiplication modulo m instead of just powering, then if we had a suitable axiom to this theory VTC0, we can actually prove the full iterated multiplication axiom. And in particular, we can prove a suitable form of Chinese remainder representation reconstruction. That's kind of the most important, most difficult part of the proof. And just to give you an idea how what is used here, kind of basic tool in the when working with this Chinese remainder representation is this formula. If we have a number x in this CRR representation modulo sequence of primes m, so this vector of small x are the residues, and the capital M is the product of the primes, then if we take and we consider the product of inverses of these primes modulo show these primes mi. This sum here is basically x divided by m plus a small integer. This integer is called the rank. Now, this identity that holds in basically all fields where these numbers are invertible with the same rank. If we interpret it in the rationals, then we can use this formula to obtain an approximation of this x divided by m by taking an approximation of this thing here. We can also interpret it to modulo m, some prime m, and then we can use it to compute x modulo m simply. So you can think about this as extending this CRR representation to a basis that has an extra prime in the basis on top of these vector of m's. Now, now we cannot directly formalize anything like this in the theory because, as I said, we cannot compute this product, we cannot form this division, and so on. But this is the guiding tool. So what we do instead is we just define approximations of the quantities involved in this formula. So, for example, we approximate this sum here by this. So we just we multiply everything by 2 to the n to get some precision. When we compute the division here and round it, we can do this. We can actually divide by small primes using this axiom, and we sum it. And then this is an approximation of 2 to the n times the sum that we had here. And from this, we get something like the rank, and something like the approximation of x over m, and something like the basis extension function. Except that everything now depends on this n that gives the precision. And then now we do a lot of work and prove all kinds of properties of these functions from first principles, and that kind of everything works in the end, and can then obtain soundness of the iterated multiplication algorithm. So so this is the end of the talk. So this is a summary. We know that VTC0 extended by iterated multiplication proves open induction and even the least element principle for sigma B0 formulas. And we do not know yet whether this iterated multiplication axiom is in fact redundant, whether it's provable in the base theory VTC0 right away. But there is some indication that it might be, so this is a work in progress. Then so far I know that it can be proved if we consider this weaker extra axiom basically. So this is all.
Okay, thank you, Emil. Now this is the clapping part. I'll do my clapping. Okay, thank you. And are there any questions?
Yeah, well, let other people go first. My question is sort of more overview historical.
So
oh, well, I'll just go. Yeah, I mean, one of the things here is that you're showing, I mean, how much one can do with very low level arithmetic. In particular, you're showing, I mean, things coming out, you're doing some analysis here, right? Lagrange's theorem, I mean, Lagrange's inversion formula. In fact, historically, yes, Lagrange actually defined a function to be a power series. But, we've seen over the years that, you can do you can do quite a bit of analysis in low level arithmetic, and here it's very fine and elegant in what you're doing. Can you go as far as things like continued fractions with this kind of machinery?
For the interruption, I lost the connection again. Sorry, can you repeat the question?
No, I was just saying, I mean, as I bring this up in part because I remember talking about it with Michalski years ago, about how much you can do, with how much analysis you can do with low-level arithmetic, with arithmetic. And but the question comes up, I mean, you're going so far, but can you do things as sophisticated or as continued fractions at this level of arithmetic?
I didn't try to look at continued fractions, but this might be actually difficult to do in these kind of theories because in VTC0 we basically cannot do any kind of sequential computation because in this TC0 we have just defined like these formulas of bounded depth, so we can iterate a function or compose functions a constant number of times, but we cannot iterate them further. We can just do things in parallel, but not sequentially. So I'm afraid that, for example, in continued fractions you cannot, for example, formalize anything like the Euclidean algorithm for GCD, because there you essentially need that at each step you look at what you got so far and continue on that. So you could define like constant number of iterations of this, but that doesn't get you very far. So I guess that it would be rather difficult to do anything with continued fractions in this theory. You probably can prove some basic things about it in a theory corresponding to polynomial time. This shouldn't be too difficult.
You have a version of a kind of intermediate value theorem there, where you show that you have to jump over zero.
Yeah, but for constant degree polynomials, so it's limited.
Very nice.
I have a question about near the beginning you had a series of complexity classes, including TC0, that were all within polynomial time, and one was included in the next. Do you know anything about whether those inclusions are strict? Right.
For most of them, this is an open problem.
Yeah.
So it's there is another class here in between AC0 and TC0, which is called ACC, which is basically a union of the classes AC0M, which are defined just like AC0, except that we allow not just